Are there generic principles in mathematical modeling of a physical process? This video is part of a course on food physics, of which this belongs to the modeling section. This is the second of a three-part series on conceptual introduction to modeling. Are there general principles for building a physics-based model? I share this not based on some deep science, but from what I learned in teaching a modeling course for more than 25 years and research for almost 40 years. These principles are listed now in no particular order, so here comes the first one. Modeling or experimentation? Do I build a model or do I go the experimental route? They of course have their relative advantages. So modeling, for example, can give us mechanistic understanding that is often very hard for the experiment. Explaining experimental results often need some model-based understanding. On the other hand, experimentation can give us a quick answer to specific situations that modeling cannot touch in speed. And modeling needs experimentation for validation purposes. So here's an example where mechanistic understanding can be useful. So in this one, it talks about a conclusion. I just happened to choose this from a study in a very random way. It is not intended to put down any work of or anybody's. But this is very typical of many studies in food. And without mechanistic understanding, we have to keep repeating such experiments. So we have to do many, many more experiments than if we had the mechanistic understanding. So it's not modeling or experimentation. It's really modeling and experimentation. Of course, we cannot do as detailed an experimentation as the most detailed modeling in the same study. That's kind of hard, but we always have to combine some modeling with experimentation to get the best of our understanding. As said elsewhere, modeling is one of the pillars of science, along with experimentation and theory. So eventually, understanding and optimization is our purpose, and it is the same with experimentation. An interesting question would be, if it is modeling and experimentation, which one comes first? That would be a good thing to think about in trying to give a general answer. In our experience, almost always the preliminary experimentation comes first. They give a qualitative understanding of the process. This could be just simple observations, but this almost is always the starting point. Based on this, we build the preliminary model, and then we compare this preliminary model against whatever little preliminary experimental data we have. This may then provide us insight into a possible need for more careful experimentation. So whether it's from this improved experimentation or from even the preliminary experimentation, we might get ideas on how to, enough insight to improve the model. Maybe we are missing some physics. So modeling and experimentation go together. General principle number 2. Models for the same process can have a range of fidelity, from very simple to very complex. Let's look at this with models that have been reported for frying. Frying models have been reported that are quite simple, like the lumped parameter model, all the way to the most complex, treating the food as porous medium with distributed evaporation. Does this mean one model is wrong and the others are right? They're all right, they're all correct, assuming they served some purpose. They're also all wrong because even the best one cannot capture literally everything that is in reality. All models are wrong, but some are useful. This is a very famous quote in the context of modeling. Now, in my personal interactions with scientists working with complex material such as food that has also biological variability, I am told repeatedly that, oh, the models cannot really predict reality exactly. Well, it does not. The models do not predict reality exactly. In fact, they cannot. This is captured in this famous line. If we ask the question, is the model true, where the truth is to be the whole truth, the answer must be no. So we have to rephrase the question. We have to ask, is the model illuminating and useful? Does it provide understanding and help us optimize and provide predictive ability? If it does, then it has served its purpose. So models don't always need to have the same fidelity. So for example, in academia, our goal is to have more detailed mechanistic understanding often. And so the models need to be of higher fidelity. And in contrast, models in industry, we often want directionality, obtain trends in optimal design, or how we can reduce time to market. So some of those models that are simpler may be good enough for some industrial implementation. And finally, modeling reduces and it does not eliminate experimentation. So our principle can be stated as the model needs to be done in a way so it's useful for the intended purpose. General principle number 3. So let's look at a modeling process which goes like this. You take a food process which is in the physical world and you write its governing equation, boundary conditions, properties, and so on, which is the mathematical analog of the physical process. Then, of course, you solve those equations and you do the design and optimization with the solution. But the very first step, going from the physical world to the governing equations and boundary conditions, that's called problem formulation. If you look at details of that step, it has parts like setting the goals, the geometry, governing equations, boundary conditions, and so on. Now, with all the advances in computing, this problem formulation step cannot be automated. It needs the physical understanding of the process to be able to make the simplifications. This is why one needs to know heat transfer before modeling a heat transfer process. Now, here is a conceptual diagram, not to be taken quantitatively, of what computing has done. Computing in the past, we would spend time on problem formulation, and then once we have formulated the problem, the governing equations and boundary conditions will be solved by writing our own code. So the solution process was really long. What the computing advances have done is to decrease the time in the solution process, or the time to do many simulations. Like here, this might have been reduced, but problem formulation still takes about the same time as in the past, because that's not automated. As an engineer or modeler, this is kind of our job security. Now here is an example of approximate distribution of effort in a modeling study. I'm going to show this using very qualitative diagram, so it's not to be taken quantitatively. It's just to make point of relative time spent in various aspects of modeling. So this one has to do with modeling rice puffing, which is quite a complex process involving multi-phase transport, large deformation, plasticity, property changes, and so on. So in that one, the time spent kind of went like this. The numerical issues, solving the complex set of equations, still takes the bulk of the effort, but problem formulation still takes a very significant portion of the time needed for the total modeling effort. This is the main point, that the problem formulation here, problem formulation takes a very, very significant part of the total effort. General principle number 4. As new computing software become available and they become more user-friendly, we may be tempted to think, now I can model this physics because I have just the software. For example, okay, I have a software for solving Maxwell's equations, so yes, I can model microwave heating of food. But computing tools do not replace physical understanding. Before using a calculator, we had to learn what multiplication means. Before knowing what is multiplication, if we try to use a calculator, it would be meaningless. A calculator simply allows us to do the complex ones faster. We should have a reasonable idea of what is meant by multiplication. In this case, for example, if I'm multiplying these two numbers, we have an idea that the result cannot be in the hundreds, or the results cannot be negative. If we get numbers like that, then we instantly know that we made a mistake in punching. Some of the same idea carries over in higher level computing. Remember, most of the software we use are primarily just equation solvers. They have no idea of the physical process that we're trying to model. So we should have an idea of what to expect. Before modeling, we should have a qualitative picture of what is it that we're modeling and have some idea of what the results should look like. This is not very different from the calculator example, where we expected the numbers, for example, could not be 100 in that multiplication, or it cannot be negative because the numbers being multiplied are both positive, like that. Just like the calculator gives us the detailed and the exact result, here the modeling gives us the quantitative details. So it's more precise, and we can run many times very easily to do what if scenarios that are very important for design. This may be very obvious, but we should remind ourselves of it. that a computer program is going to give what we told it to give, not what we are looking for. So what does all this mean? Because we can make mistakes, and the way fundamentally this type of solution works, the computer can make lots of different errors. GIGO, or garbage in, garbage out, is a real possibility. It happens all the time, and we need to be watching out for it. So we must continuously verify, which is a step different from a more detailed step of validation. At least informally, we must verify the solution against what we expect from common sense or simpler understanding. What all this means is just like punching calculator buttons. In using computing software, we need to have similar basic understanding of the process, so we know when a solution is obviously wrong. So here in this kind of computing, of course, is the added complexity in relation to this calculator example, is that uh, the solution process can fundamentally give you wrong answers. That's just the nature of the solution, even when you provided the correct input, like punching the right button on the calculator. Even if you did that, you could get wrong answer. So we must be watching out all the time. Because of this need, we should not get into modeling of physics just because we have a computing software available for that physics. We need to first learn enough of that physics. General principle number 5. As already mentioned, many levels of engineering analysis or modeling are possible. For example, we can start from scientific common sense, sort of the lowest level of understanding, then move on to qualitative understanding from experiment or very simple models. Then we move on to restricted solutions for which analytical solutions are possible, and finally all the way to numerical solutions of the kind we're talking about here. Where do we start? We start from the simplest one that captures the essential physics. So this quote from Einstein can be the most important slide in the context of modeling. Everything should be made as simple as possible, but no simpler. So simplification is so critical in modeling and in its first step in the problem's formulation. Certain complications simply do not contribute appreciably to results. There's an interesting statement in modeling called consider a spherical cow. A cow looks nothing but a sphere, but can I get some essential understanding about some aspect of it, even if we consider it as a sphere? Such approximations are possible. In fact, some critical mechanisms can stand out more clearly without some of the details. So that was to make the point as simple as possible. Now I will try to show an example when we simplified too much. To give you a little background, here is a problem in my early career where we were looking at why pizza, when heated in a conventional hot air oven, the crust stays crispy. But when heated in a microwave oven, why does the crust get soggy? In hot air heating, we remove moisture from the surface, and then moisture from the inside comes to the surface only in relation to what has been removed. So the moisture removal very much keeps up with moisture coming to the surface because moisture removal is the driving force. But in microwave heating, in addition to this process, that yes, there is some moisture diffusion and there is moisture removal, in addition to that, there is pressure driven flow. So pressure driven flow is an additional mechanism that pushes water or vapor toward the surface. This pressure-driven flow is driven by gas pressure and not by concentration as in diffusion. So this mechanism, if it is lumped, this pressure-driven flow mechanism, if it is lumped with diffusion, it will simply not work. So this is an example of simplifying too much by including the pressure-driven flow into some sort of an effective diffusivity. If we simplify too much, it loses some critical physics. We will never be able to predict the soggy surface with just effective diffusivity. So this simplification is always a balancing act. If we make the model too complex, it could take forever to compute, or it can make it much harder to debug. On the other hand, if we make the model too simple, it could miss the main physics. Then there is like no point in doing the model. It doesn't represent the reality. Or if we simplify it too much, it cannot be used as effectively for prediction purposes because it doesn't work for a larger range of parameters and so on. So start from the simplest and build in complexities one at a time. There are, of course, many ways to do this, and what I am about to share are some steps to possibly achieve this, but there are many ways. So start from constant properties, boundary conditions, etc. Even if they're varying with time, with composition, we can start from constant values initially. Unless necessary, we should not get into a 3D geometry. We should try with 2D first. Then we don't need to include complex fluid flow unless that is the critical part of the modeling. And we use a coarse mesh to get started. And then for a transient problem, we don't try the entire time duration initially. We just try a few time steps. It may be possible to do a steady state analysis before doing the transient. These are just a few tips to kind of start from the simplest and build in complexities. General principles in modeling number 6. Modeling food processes has unique challenges that need careful attention throughout the modeling process. Food is structurally complex and it has a very complex relationship between the typical properties that we can predict in modeling and the all-important sensory qualities. Also, being a biological material, it has high variability. During processing, food also undergoes massive changes. So think of how a dough becomes bread, and these massive changes during processing need to be captured in the model. Otherwise, the model will not be realistic. Then the engineering studies looking at detailed physics with all the mechanisms, these kinds of studies have been not rare or maybe even rare compared to the total amount of studies that we have in food. So there is less unknown in this kind of modeling. Now, quite often food processes involve multi-physics. So for example, let's say microwave drying. That would involve fluid flow, heat transfer, electromagnetics, solid mechanics, because it shrinks as it dries. So that those are all you know very different physics. And so to do a realistic model, one needs to include many of these physics, and so that makes it quite complex. And very related to that, if we have to handle these many different physics, then we need multidisciplinary human resource background in a team or the same person, which is even harder to pick up these different disciplines. So that certainly makes it harder. And finally, the raw material cost in case of food is lower than many other engineering materials. So this can make it less sort of a justifiable to get into detailed modeling in some food processes. Thus, we need to be carefully considering these aspects as they affect the final quality of what we predict from the model. General principles in modeling, number 7. Lately, we have been hearing more about machine learning, which is expected to go up in the future. Mechanistic or physics-based models, the kind that we have been discussing, provide the causality or the relationship between cause and effect that would be missing from machine learning approaches. That is the big plus for mechanistic model. Of course, there are other advantages. However, the requirement of a deep understanding of the system, many simplifying assumptions, and the overall simplicity may prohibit the more universal predictions achievable by machine learning. Machine learning can more easily adapt to more complex and nonlinear relationships and its new data. More and more, it seems hybrid models that are combinations of mechanistic models and machine learning, like physics-informed machine learning, is the way to go. There are other ways to combine the two, and I will share with you shortly one of those. So mechanistic models are simply difficult for some complex and specific systems. And for these, the data-driven models would be better choice. Here's an example I happen to pick very randomly from research literature. So this one is a study of a complex food system that is asking for some very specific answers. This is difficult to approach mechanistically. Here, a full-blown mechanistic model is unlikely to be the way to go, and data-driven model would be a better choice that will go a lot quicker. Here is an example of combining mechanistic and machine learning model. Here, the machine learning model was developed from a mechanistic model. You can see the obvious advantages. The machine learning model takes 6 seconds, whereas the mechanistic model to predict some of the same thing would take 6 hours. So how do we do this? Here's a quick note. So we first build a mechanistic model, in this case a porous media model for drying, and from that we generate simulation results like moisture, temperature, and then we use these simulation results to build and train a neural network model. And then once trained, then the neural network model replaces the mechanistic model for many intended uses. To complete this as one of the principles to be followed in modeling, we see that mechanistic, machine learning, hybrid, or their combination really depend on several factors like the goal, the computing resources available, the human resources available, and so on. So there is no universal answer. General principles in modeling number 8, which is also the last one we have in this video. In modeling, we start from a reality of our interest, which would be the food process we want to model, and we replace that with governing equations and boundary conditions, which is our mathematical model, and then we solve those governing equations and boundary conditions in using a software, so that becomes our computer model. So the output from those computer models, the simulations have errors and uncertainties that are committed at each one of these steps. So a model must be validated. That is very, very critical in modeling. So this validation cannot be an afterthought. We need to have a plan for validation as we even get started into modeling. We often try to relate to available experimental results, but we need to be aware that they are often not for the exact conditions we need, and therefore that validation does not always guarantee validation for the exact situation we are modeling. Also, as we validate against experimental results, we should also remember that experimental results also have errors. At the same time, we cannot possibly validate every result that we generate from the simulation. Of course, we still need ways to develop confidence in any result that we generate, any predictions that we do, for example, using qualitative comparisons. But if we have to validate experimentally every single result that we generate in the simulation, then we might wonder what was the reason to develop the model in the first place. So to model and validate every single result experimentally, it will be more than twice the work, and it's often not feasible. So here we summarize the 8 principles that were mentioned in this video. Of course, one can think of many more principles. So the first one we mentioned was that modeling is one of the pillars of science, along with experiment and theory. Then a model simply needs to be useful. If it were useful, then it was worth it. One of the primary steps in modeling is problem formulation, where we go from a physical system to a mathematical description, and this is one of the most critical steps, and it requires significant understanding and time. So physical understanding of a system is critical. One should not get into modeling a physics without first developing a good physical knowledge of that system. And no matter how much resources we have, computing resources or expertise, it is critical to simplify the system. And throw out unnecessary details. Otherwise, we will definitely run into problem or spend more effort than needed. And food is complex, has many challenges, and we need to be aware of them throughout the modeling process. Now, mechanistic and physics-based models, they serve complementary purposes, and their combination would be the way to go in the future, and it is what is most appropriate for a situation. It just depends on the situation. And finally, there are errors and uncertainties that are built into a model, and therefore validation of modeling results, validation of the simulation results is critical. So this video talked about some of the principles, general principles in modeling, and a video before that talked about the very rationale for getting into modeling. The following video would be talking about the steps, the generic steps involved in a mechanistic modeling process.